The accelerated twin paradox. In this episode, the smuggled assumption. Mach's principle of relativity. First, Mach's principle of relativity, the idea that all motion is relative. Yes, this is Mach's principle, not Einstein's. Einstein said something different. It is taken as axiomatic that when the relative speed of Bob and Alice is constant, time dilation applies. Alice, who stays at home, sees Bob's clock go slow. So except at the moment of reversal of velocity, the turnaround at Proxima, Bob's clock goes slow in the view of Alice. When Bob returns, he must have experienced less time, says Alice. The problem is that this equally applies to Bob, except during the moment of turnaround, Bob sees Alice's clock go slow. So why doesn't Bob see Alice as having experienced less time? If all motion was relative, then when Bob returns to the Earth, there should be no way to distinguish one twin as having moved. To make this clear, consider this from the point of view of Charlie, who moves so as to be exactly halfway between Alice and Bob. Charlie sees Alice and Bob move away and return as mirror images of each other. We would expect the time on each clock to be the same, even if different from Charlie's. Now do the same exercise without Charlie. If Alice sees Bob's clock as showing an earlier time, then Bob should see Alice's clock as showing an earlier time. But at most one of these clocks can be ahead. In fact, if all motion is relative, this shows, curiously, that time dilation in this sense cannot occur. However, it is part of the mechanics of relativity that observers do agree on the things that can be measured from a still shot of a single point in space and time. Unpack the logic here. The clocks do or do not agree back on Earth when Bob returns. Either one clock is ahead or the other is ahead. This is not to be argued. We're not doing quantum mechanics here, one or the other and not both. But the symmetry implies that if Alice's clock is ahead, then so is Bob's. The only resolution is that they agree. And so, if all motion is relative, then all clocks agree when they are next to each other, and this allows the establishment of an effectively absolute time, and so there is no time dilation. The conclusion is that in relativity not all motion is relative. In particular, acceleration is not relative. Review of absolute acceleration. Relative acceleration can be measured, obviously. It is just the second temporal derivative of the position coordinates. But to validly say that acceleration is relative would require that there does not exist a method for establishing any kind of universal standard acceleration. In our universe there is such a standard. The universal zero for acceleration is determined by if you feel no force like gravity. If there is no tendency for objects to fly off from where they are put, then your frame is not accelerating. If your frame is not accelerating, then by definition your frame is inertial. This has a real physical meaning and can be established while enclosed in a shipping container with no way to look out. Do things fall or not? So the analysis of the twin problem has to use acceleration, and acceleration is not relative. But this in itself does not resolve the twin paradox. It means that the acceleration has something to do with the breaking of symmetry. But exactly who is accelerating, and why does it have the effect it does? And even if Bob has his rockets on, or gets his rockets off, it does not explain why Bob feels absolute rather than relative acceleration in relativistic terms to interact with time dilation. This is deeper than it sounds, and is actually a problem for advanced general relativity and the quantum gravity theory, and no one knows how that works. So, keeping to a long-established tradition in science, since I cannot answer the tough question that really matters, I will instead answer another question that sounds similar. Not why in the sense of dynamics, but just what happens when the absolute accelerator has been identified. This will also demonstrate that in relativity, saying that someone is accelerating and by how much and in what direction is not enough. You also have to state effectively the surface that they accelerate with respect to, in one-dimensional space, the point about which they accelerate. This rather weird comment will be explained as the discussion proceeds. Some logical pragmatics. Now we introduce a matter of logical pragmatics. Science is always an approximation. It even casually and commonly approximates things that are known more accurately, for the simple reason that taking everything into account can make it difficult to impossible in any practical sense to actually reason with the topic at hand. If you plot the speed of your car as a function of time, you'd expect there to be no gaps in the graph. If Bob accelerated all the time, then it would be hard to apply special relativity, since the rules as given apply only to non-accelerating frames. So we give Bob a sudden step change in velocity in Alice's frame. That means that Alice also has a step change in velocity in Bob's frame. Continuously varying velocity with no impulse of acceleration is more physically reasonable, but despite not knowing who gets squished, the logical reasoning about the acceleration is more convenient with a sudden change in velocity, since there is only one point that is not handled by the relativity of velocity rule. This is the turnaround at Proxima Centauri. Anyway, in some sense we are required to look at a single impulse before extending that to a more general case. The continuous velocity case is in many ways more interesting, but this sudden change from outward to inward motion is the common context of the discussion of the twin paradox. The smuggled assumption. Right back at the start of all this, I said that the normal description of the twin paradox smuggled in an extra assumption. What is the extra assumption? It is assuming that the clocks cannot make a step change during acceleration. A step change is a sudden change, such as Alice's clock showing 1 p.m. just before 5 p.m. on Bob's clock, and then showing 3 p.m. just after. If this happens, we call the behaviour discontinuous. If it is not, then the behaviour is continuous. If the times cannot make a step change, then the time difference over the whole trip can ignore the moment of acceleration, and the contradiction arises that both Bob and Alice see each other as having experienced less time. Since this does not happen, there must be a step change. Try a simple case. Suppose that Bob does not undergo a step change in time in Alice's frame, but Alice undergoes a step change in Bob's frame. Assuming no contradiction, then Bob has to find that Alice, although her clock went slow except at the turnaround, has a time that is ahead of Bob when he returns. Alice experienced less time in Bob's frame during the coasting part of the trip. Hence, Alice must have experienced a step change into the future that more than compensates for the slow rate during the trip. If there are no step changes, then there is a direct mathematical contradiction. But if there are step changes, it is clear that the experience of Alice and Bob can be reconciled. The problem remains as to why Alice's time in Bob's frame should jump, while Bob's time in Alice's frame did not. Relativity of simultaneity. This really comes down to a discussion of the relativity of simultaneity. To understand what is going on in the twin paradox, one must grok that simultaneity is relative. Start with the two ideas that many people have in mind when they think of relativity, that velocity is relative and that people see other people's clocks as going slow. Alice places two drop boxes 1 light year apart on the ground. Bob speeds past at almost the speed of light and drops a note off at each drop box, indicating his time. Since Bob is almost the speed of light in Alice's frame, Alice will see Bob's clock as being slow. But Bob sees Alice's drop box speeding off in the other direction, close to the speed of light. Since the drop boxes are at high speed, Bob sees the distance between them as contracted, say to about 1 light month. And that means that it only takes about a month between the 2 times that Bob dropped off a note. However, since Alice is going fast in Bob's frame, Bob must see Alice's clock as going slowly. So in the month that Bob waits for the drop boxes to pass by, he sees Alice's clock only register a few days passing. Can we be objective about this? Alice says the distance is a light year. Bob says it is a light month. Okay, they have a different way of measuring. Alice says 1 light year later, Bob says 1 month. Again, different ways of measuring. But Bob says that Alice's clock only moved a few days while he did the trip. This seems to be in conflict in a more crucial manner. The situation is biased in that the drop boxes are stationary in Alice's frame, so the light year and the light month distances are fairly simple relativity. Alice sees the rest length and Bob sees the at speed length. But that disagreement about Alice's clock, how does that even make sense? Use the rule that agreement will occur about things that happen at one place and one time. Alice says that as Bob passes the first drop box, her clock reads 0 time, and Bob agrees. Bob says his clock reads 0 time, and Alice agrees. As Bob passes the second drop box, he says his clock reads 1 month. Alice must agree. His story is that the distance is 1 light month. Her story is that his clock is slow. But while they disagree on why, they agree on what happens. But as Bob passes the second drop box, he claims that Alice's clock is reading only a few days, while Alice says that as Bob passes the second drop box, her clock is reading 1 whole year later. The resolution is that this is comparing things that did not happen at the same time and place. You think you can do these things, but you just can't, Nemo. When Bob passes the second drop box, Alice is some distance away. So what is being compared is what Alice thinks her clock is showing when a distant Bob passes the second drop box, and Bob is comparing what a distant Alice's clock is showing as he passes the second drop box, not the same time and place. Place a clock on the ground near to the second drop box. Alice synchronizes this clock with her clock. It shows 1 year has passed when Bob passes the second drop box, and since that happens at one place and time, Bob has to agree. But this is a different clock. Bob says that the clock next to Alice shows only a few days, so Bob is saying that these 2 clocks of Alice are not synchronized. And it is this last point that is the key to most relativistic puzzles. Alice says that the event of her clock showing 1 year coincided with Bob being at the drop-off. Bob says that it was Alice's clock showing 3 days, but he agrees that the drop-off clock showed a year. Why this is happening is the relativity of simultaneity. Not only does the other observer see your time as going slow, but also that your clocks are not synchronized. You think that your clocks are synchronized. They do not. They think that their clocks are synchronized, and you think that they are not. A mathematical point. I would like to make a mathematical point. The Lorentz transformation says that the time in Alice's frame at some specific time and specific place in Bob's frame is computed as a linear combination of that time and that place. For example, it might be 5 times Bob's distance plus 3 times Bob's time. That means that the rate of passage of time in Alice's frame, as measured by Bob, depends on where Bob measures it. At a specific point in Bob's frame, meaning that Bob looks out the window and reads the time that is showing on the Alice clock that is just passing as he looks out, the time will pass very rapidly, not slowly. The relative rate is gamma. This relativistic factor gamma goes to infinity as the relative velocity approaches the speed of light. Looking out the window at the clocks as they pass, Bob will see Alice's time advance very quickly indeed. This is how, in just 1 month of Bob's time, the time out the window in Alice's frame advances all the way from 0 to an entire year. In just 1 month of Bob's time. The relative rate of passing of time, as Bob judges Alice's clocks, depends on where exactly one considers Alice's time. To get the slowdown, one actually has to substitute a position that is moving in Bob's frame. So while the time in Alice's frame, measured right next to Bob, advances very quickly, the time where Alice is advances very slowly. That occurs because Alice is rapidly receding into the distance to Bob's rear. While there is a strong psychological tendency to interpret the idea of the rate at which Bob measures time passing in the Alice's frame by assuming he will watch a spot that is stationary in the Alice frame, indeed typically that his voyeuristic eyes are fixated on Alice herself, this is not really the only interpretation. In classical mechanics, the issue does not come up at all. In classical mechanics, it does not matter what speed a material or conceptual point is moving, the passage of time is the same. But in relativity, the speed of the point where time is being measured does affect the details of time, as does the relative speed between the two frames. The question of the path of the point for which the passage of time is to be measured is now a factor. That means that one can consider a point that is stationary in Alice's frame, or stationary in Bob's frame, or any other path, including one that exceeds the speed of light, and so on, as part of an entirely valid discussion of the implications of relativity. Different paths result in different ideas of how time in Alice's frame changes. Velocity is relative. There is no reason to say that one is more right than the other. It is a choice, and for a correct discussion that choice has to be announced. Relativity of simultaneity is the core point that prevents there being any sense of absolute time. Time dilation does not mean that someone's clocks go fast and someone else's clocks go slow in any absolute sense. There is, in fact, no absolute sense of time. This should be emphasized. There is no cosmic absolute time. There is only time as experienced in particular frames. Different people see other people's clocks as going at different rates in an unsynchronized and possibly erratic manner. From Bob's point of view, the clock at the second drop box did go slow. But also Bob says it was set a bit short of a year ahead of the correct time. During the month it took for the second drop box to arrive, Bob says the clock did indeed go slowly, registering only a few days and reaching 1 year as he passed. This can be summarized by pointing out that in Bob's frame, Alice's time does not depend just on Bob's time, but also where in Bob's frame the time is measured. This is the relativity of simultaneity. In summary, as Bob passes Alice, he sees her clock as time equals 0, like his. However, he sees the drop-off clock as showing a few days less than a year. When he arrives at the drop-off a full month later, both Alice's clock and the drop-off clock have gone slow, so now Alice's clock says a few days and the drop-off clock shows a full year. Finally, breaking the fourth wall, I hope that you liked this discussion and would like to hear more. To facilitate this, like a street performer, I now pass the hat around. Please like, subscribe and share this video with your friends or your enemies or anyone randomly off the street if you feel that way inclined. This will give me the opportunity to produce more of these, and if you feel that anything was unclear or incorrect, or you want to know my opinion on some detail or other, please leave a comment to that effect. Thank you. There are some issues that I haven't really resolved yet, and there's a fair amount of distance to go. I will try to produce a simple version of the whole thing sometime soon.